Welcome everyone to our week 3 module 1 course. Last few weeks we have introduced you the concept of solar photovoltaics, and we have learned that how a basic solar cell work. We also learned that a solar cell is nothing but a p-n junction semiconductor diode where n side is very narrow and heavily doped. But in many occasions we can represent these solar cells by an equivalent model. Equivalent model means you represent the solar cell in terms of resistance, capacitance, which also control the behavior of the solar cells. Today we will learn that in details and different parameters associated with the solar cell technology and the sources of loss for efficiency in a solar cell. Here we are showing the equivalent model of a solar cell. As you can see, the first diagram, the equation, the figure 1 is the ideal model of a p-n junction solar cell. Here we have a current source IPH is this one, which is connected in parallel with a diode, and then since this is an ideal model, so there is no resistance. But in real cell or in practical solar cell, there are different source of resistance. It can come due to the metallic contact of the solar cell with the semiconductor, or it can come due to the crystallographic defects which originates due to the semiconductor growing. So, because of all this, there can be different source of resistance in this circuit. So, we can put the resistance in the circuit either as a series as shown it here, or either as a parallel or as a shunt resistance as shown it here. So, if we connect this series resistance and shunt resistance along with this photocurrent source and the diode current source, then it makes the equivalent circuit of a real solar cell. Now, this equivalent model of a real solar cell has the following parameters. The first one is a current source or current generator, which is generating a amount of current IPH. Now, this amount of current is coming through here. Now, it sees there are two different paths. One path is through the diode and another path goes through this way. So, the amount of the diode current is ID, which is in the absence of the light, and then the rest of the current it flows through here. Now, it can divide it through RS and it can divide it through RP. Finally, the total photovoltaic current IPV that goes to the outside load. Now, as you can see from the circuit diagram, that series resistance as small as possible, that will be good for us. Similarly, since this RP or the parallel resistance connected as a shunt resistance here, its value as high as possible, that will be good for us. But what comes from the series resistance, or what contributes to the origin of series resistance and shunt resistance? So, series resistance is a ohmic resistance in a solar cell. It comes due to the metallic contact, or more precisely metal and semiconductor junction. Let us consider this is our solar cell where the n side is narrow and heavily doped, so that the depletion regions extend inside the p regions. To complete a solar cell, we put a metallic contact on the front end and an ohmic back contact at the back end. Now, this metallic contact made a Schottky kind of barrier at this metal semiconductor interface. Now, this Schottky kind of barrier, like they contributes to some kind of resistance, and that resistance is the series resistance. On the other hand, we have parallel resistance or shunt resistance, which is mainly due to the crystallographic defect. Now, let us for example, we have a silicon solar cell. Now, when we grow this silicon crystal, there can be lot of defects or crystallographic defects can originate during this growth process, and that defects actually behaves like a charge carrier recombination sites. In addition to that, during the growth of this crystal, there can be lot of grain boundary which appears in the circuit. Now, this grain boundary also acts like a charge carrier recombination sites. So, because of this crystallographic defects and the grain boundary, we get some kind of resistance in the solar cell, and that resistance is contributing to the shunt resistance. So, as you can see now, for an ideal solar cell, the series resistance should be 0 and shunt resistance should be infinite. In many of the cases, for an ideal solar cell does not behave in a practical way as we get the power from them, or in more precisely, the behavior of a practical solar cell in many times different than an ideal solar cells. For example, if we draw the IV characteristics of a solar cell, then it should looks like a perfect square. But we do not get that perfect square in the real life when we record the IV characteristics. Now, this deviation of the real solar cell from an ideal solar cell is described in terms of a quality factor, and that quality factor is called fill factor. So, for comparing maximum obtained power and maximum theoretical obtained power, we define the fill factor. By definition, fill factor is the maximum power, that is the Im times Vm, the maximum current times the maximum voltage, divided by maximum theoretical power which we get from the circuit, that is short circuit current and open circuit voltage. So, Im Vm, that is the maximum obtained power from the device, which is like the maximum power which we can get from the device if the device is an ideal solar cell. But in reality what we get is that ISC times VOC, that short circuit current times the open circuit voltage. So, the maximum current and the maximum voltage we cannot record. What we record is the short circuit current and the open circuit voltage. If we draw an IV characteristics here, so if this is my current axis and this is my voltage axis, so we know that this looks like this. The point where the IV curve intersects the I axis, that is gives my the short circuit current. Obviously, at the short circuit current voltage V is equal to 0. Whereas, this IV curve where it intersects the V axis, that gives us the open circuit voltage. At that open circuit voltage or VOC, the current I, current I is equal to, instead of short circuit we can just call it as a current, that current I is equal to 0. So, the power delivered from this solar cell can be obtained by integrating the area under this IV curve, or we can get the power P output by multiplying the y coordinate, that is ISC times VOC, or short circuit current times the open circuit voltage. Now, typically these fill factor values are in a range from 17 to 85% and depend on the device structure. Now, if this curve is a perfect square, not like this, but rather imagine this curve have a shape like a perfect square, and now this perfect square they intersects the I axis at this point Im and on the V axis at a point Vm. So, what will be the power obtained in the ideal case? That is the area under this perfect square, or I can draw it in other direction like this. So, what will be the maximum power in that case? That will be Im times Vm, but we do not get the Im times Vm because of the series resistance and the shunt resistance. We get a deviation from the maximum power output. What we really get is the ISC times VOC. So, to quantify this deviation from the ideal solar cell, we define the fill factor. Basically, it is about the squareness of the IV curve of the solar cell and arises due to the resistive loss in solar cells. Is represented in terms of percentage. So, as the square curve deviates from its square nature, we get more and more value for the fill factor. So, like let us say we got a curve like this IV, so it is not a perfect square. How much deviation I got? I got a deviation that I quantify in terms of fill factor, which is Im times Vm divided by IOC into VOC. That expression quantifies this deviation from a square or ideal square curve, IV curve. Now, if I multiply my output power, which is I short circuit times V open circuit, into the fill factor, so then what I get is the power output from a real solar cell. So, the power output from a real solar cell, now if you divide by power input, that is the how much amount of power I have put in the solar cell, which is coming from the solar radiation. So, then I have to divide this IOC into VOC into fill factor by P input. But what is this output power by input power? This is nothing but the efficiency of a solar cell. So, the efficiency of a solar cell eta is defined as the output power to the input power. We will come to this point later on in details, and as you can say that this efficiency is equal to the short circuit current times open circuit voltage times fill factor divided by P input. So, if we have been given the input value from the IV characteristics, we can calculate what is ISC value, what is VOC value, and what is fill factor value, and in principle we can calculate the efficiency of a solar cell. Now P input, or the amount of power we are putting inside a solar cell, that can vary significantly. Even as you have learned that sun moves across the earth, the intensity which reaches on the earth's surface, that varies over the day times. So if somebody wants to define the efficiency of the solar cell, one has to be very consistent about how much input power he or she is using. Let us say somebody is measuring the solar cell efficiency for an input power of 500 watt per meter square, and another person is measuring for 1500 watt per meter square. Obviously, even if we keep ISC, VOC and FF as the same, since now P input is different for the same values of the IV curve, for different values of the input power, my efficiency will be different. So to remove this inconsistency, people have come to a conclusion that whenever we will report the efficiency of a solar cell, we will report that for a particular input power, and that is called the AM 1.5 solar radiation. AM 1.5 solar radiation corresponds to 1000 watt per meter square input power. So if we put that value of the P input in the input value, and from a solar cell if we measure the short circuit current, open circuit voltage as well as fill factor, then we can calculate what is the efficiency of a solar cell. And this job more often is done by an instrument which is called solar simulator. It is also worthwhile to mention that, like, the fill factor value can tell you how good the quality of the solar cell. In ideal case, the value of fill factor must be 100%. That means there should not be any deviation from the square nature. But in real solar cell there can be deviation, and where this deviation is coming from? Due to the resistance. What kind of resistance? It can be series resistance or it can be shunt resistance. What contribute to the resistance? It can be metal semiconductor contact or the defect states which comes due to the growth of the semiconductor. Now this is all the experimental parameters or the experimental efficacy. So because of that, we very often we get a series resistance or shunt resistance in the circuit, and that contribute to the deviation of the IV curve from a ideal IV curve. But it is not feasible to have a square IV curve always. There are always some losses which reduce the value of fill factor. Significantly, if the fill factor value is very less, then the efficiency of the solar cell will also be very less. The best value of fill factor that can be obtained from a solar cell, it can be empirically written as a function of the open circuit voltage. So you can write the fill factor as the V open circuit or open circuit voltage minus log of V open circuit plus 0.72 divided by V open circuit plus 1. So that means if we know the open circuit voltage, we can calculate what is the value of the fill factor, where V open circuit voltage is VOC divided by KT by Q. It is the open circuit voltage normalized to thermal voltage. So this utilized VOC is not the open circuit voltage, but it is normalized open circuit voltage. With which we have normalized it? We have normalized it with thermal voltage. And what is the value of thermal voltage? It is the Boltzmann constant time temperature divided by the charge of an electron. So if we know what is the value of the VOC or the open circuit voltage, then we can calculate what is the value of a fill factor. So as we said, like efficiency, it is defined as the ratio of the power output to power input. Like all engines, they provide some kind of power output when you put some power input. Solar cell also take this power input from the solar radiation, and what it does, like it converts the light energy to the electrical energy, and this electrical energy is nothing but comes in a terms of the current and voltage, and this product of current and voltage we call it as a power. The power output is the maximum power point PM of a solar cell, and input power is the power of solar radiation, P radiation. According to international standard for characteristics of solar cells, P radiation is equal to 1000 milliwatt per centimeter square or 1000 watt per meter square. Now as I have also mentioned before, that if the input value of the power is not same while reporting the efficiency of a solar cell, there can be several inconsistency. For example, if somebody make a solar cell and measure the efficiency for 1000 watt per meter square like AM 1.5, and some other person make the same solar cell but report the efficiency for 500 watt per meter square, then these two value will be significantly different. To avoid this inconsistency, we always keep the input power at 1000 watt per meter square. So eta, or the efficiency of a solar cell, is defined as the maximum power divided by the input power, which is nothing but the P solar radiation. Now what is PM? Pm is Vm times Im, that is the maximum voltage times maximum current. And we can write this maximum voltage times maximum current as open circuit voltage times short circuit current times fill factor divided by P radiation, because we have just learned that fill factor is equal to Vm Im divided by Voc into Isc. So, Vm Im, this is this part, can be written as Voc times Isc times fill factor. That is exactly what we have written here, open circuit voltage into short circuit current into fill factor divided by the P radiation. If we multiply it by 100, we will get the efficiency in 100. Now, because of the series resistance and shunt resistance, fill factor value can change significantly. Now, the series and shunt resistance mainly affect the fill factor of the solar cell, which in turn affects the efficiency of a solar cell. The series resistance is the sum of the resistance due to all components that come in the path of the current. So, whenever current flows in a circuit, whatever the source of resistance it feels while going to the electrode, that acts as a series resistance. This includes the base, emitter, semiconductor metal contact and resistance of the metal contact. So, that is why sometimes we make a finger electrode to minimize the series resistance as much as possible. The shunt resistance is due to the leakage current across the PN junction. Now, what will happen if the series resistance changes and if the shunt resistance changes? So, that will directly affect the IV curve. As you can see here, the IV characteristics, like the fill factor value is showing for series resistance value 0. When the series resistance value is 0, then you see that this curve is this blue curve, this one. When the series resistance is 10 ohm centimeter square, then this portion of the curve is changing. So, you see that the red curve is bending before a perfect knee, while like it is a 20 ohm per centimeter square, it has bended like this. So, if it is high, like let us say 50 ohm per centimeter square, it will be like this. If it is too high, so then it will be like this. So, if we get a solar cell where the IV characteristics is like that, so we mean that the series resistance of this device is very, very high. Now, what will be the contribution of the shunt resistance? So, if the series resistance is modulating this part, so we can consider the shunt resistance, obviously it will contribute to the other part. So, for a infinite shunt resistance, the IV characteristics should be like a blue curve, like this. But if I have the shunt resistance value like 1000 ohm per centimeter square, then it is a red curve like this. So, it falls up rapidly from the ideal curve. Then if it is 500 ohm per centimeter square, then it falls up more rapidly. So, as you go lower and lower values of the shunt resistance, the x axis near about part of the IV curve falls up very quickly. So, in the same curve here, if the shunt resistance is very, very low, so this graph will be like this. So, if somebody recorded a solar cell IV curve and this is like that, so what do you mean from that? That series resistance value is very, very high and shunt resistance value is very, very low. What we need? Very, very low series resistance, ideally 0, and very high shunt resistance, ideally infinite. If the series resistance value is anything more than 0, then we have learnt that this part of the curve is going to change, and if the shunt resistance values is less than the infinite value or as small as it will be, this part of the curve is going to change. So, by looking at IV characteristics, an engineer can comment that whether the series resistance or shunt resistance is contributing to the performance of the devices, and they can take precaution measures to take care for that. Now, what is the effect of solar radiation on efficiency? It can safely be assumed that short circuit current is proportional to the intensity of radiation, that we have learned earlier, that I short circuit is equal to minus K into I, where I is the intensity of the radiation and K is a geometric factor. Also, the VOC or the open circuit voltage we can write as open circuit voltage is equal to KT by Q log IL by I naught plus 1 is equal to KT by Q log IL by I naught. Now, what is K? K is the Boltzmann constant, T is the temperature and Q is the charge of the electron. So, this part is the thermal voltage times log IL by I naught, that is the load current, divided by I0 plus 1, or one can simplify if the IL very greater than IO. So, then we can write it is KT by Q log IL by IO. Using the our approximation, the equation for cell efficiency can be written as eta is equal to I short circuit into open circuit into fill factor divided by the input power. Now, if we plug in the value of the open circuit voltage from here, what I will get? It is KT by Q log IL by I naught into fill factor into the short circuit current divided by the P input. If the solar intensity decrease, the efficiency of a solar cell decrease, so decrease due to the decrease in the VOC with the IL. So, if VOC changes or the open circuit voltage changes, then the efficiency of the solar cell also changes. Now, temperature also plays a very important role in measuring the efficiency of a solar cell. For example, the temperature dependency of solar cell it comes due to the changes in the VOC as we change the temperature, and we can deduce an expression for that. So, as we know that current in a solar cell, that can be written as a combination of two parts. One is the photocurrent minus IPH and another is the diode current I naught e to the power EV by eta KT minus 1. Under open circuit condition, there is a voltage V open circuit at the output terminals. So, when I is equal to 0 here, then IPH is equal to exponential EVOC by eta KT minus 1, because we have considered this term is equal to 0 when we are considering the open circuit condition. Open circuit conditions means the voltage developed across the device is VOC, but what is the current? Current is 0. Now, if I put I is equal to 0, so this terms will come on the left hand side, giving you IPH is exponential EVOC by eta KT minus 1. And then the value of VOC comes out to be eta KT by E ln of IPH by I naught. So, we know what is the photocurrent, we know what is the diode current. So, what all we used to know the efficiency of the solar cell. So, or in other way, if we know the VOC, we can find the efficiency, if we find the efficiency, we can know the VOC. So, for a given photocurrent and for a given temperature, the value of the open circuit voltage and the efficiency, they are proportional. Now, if we put it in some different way, the open circuit voltage depends on the temperature. So, from here we can write that VOC is proportional to T. So, that means if VOC changes, then T will changes, and if T changes, then the efficiency will also be changes. So, here eta is the diode ideality factor and varies between 1 and 2 for semiconductors. So, EVOC by KT is log IPH by I naught at two different temperatures. Let us say one temperature is T1 and another temperature is T2, but the illumination is same or the intensity of the solar radiation is same, but the temperature is different. Now, what will happen in this case? In one case it will be T2, another case it will be T1. So, we can write it EVOC2 by KT2 minus EVOC1 divided by KT1 is equal to ln IPH2 by I naught minus ln IPH1 by I naught. Now, if I write this EVOC2 by KT2 minus EVOC1 by KT1, so since this terms and this term is same, so we can divide the term inside the bracket of the ln and get ln I01 divided by I02 or I1 by I2, right. So, VOC2 by KT2 minus EVOC1 by KT1 is equal to log, we can also write this, what is IO, what is the diode reverse saturation current, that is proportional to the intrinsic carrier concentrations. So, we can also write in terms of intrinsic carrier concentration. So, instead of this I, we can also write in terms of the Ni square. So, that is what we have written here, ln Ni1 square divided by Ni2 square. Now, intrinsic carrier concentration heavily depend on temperature. We know that Ni square is Nc times Nv into e to the power minus Eg by Kt, law of mass action, if we remember, where Eg is the band gap and T is the temperature. So, then EVOC2 by KT2 minus EVOC1 by KT1 is equal to Eg by K 1 by T2 minus 1 by T1, or if we take K as a common from here, this K and this K and this K cancels out, giving you VOC2 by T2 minus VOC1 by T1 is equal to Eg by E. So, this E we are taking out in the right hand side into 1 over T2 minus 1 over T1, or you get VOC2 is equal to VOC1 T2 by T1 plus Eg by E 1 minus T2 by T1. Okay. So, if we measure the temperature T1 and the open circuit voltage at VOC1, and if we measure the temperature T2 and the corresponding open circuit voltage is VOC2. So, VOC2 is related to VOC1 by this equation. So, what it depends on? It depends on the temperature ratio and it depends on the band gap. So, if we keep the band gap fixed, that is for a same material, it depends totally on the temperature T2 by T1 ratio. So, if there is an increase in the temperature from T1 to T2, the voltage will decrease from VOC1 to VOC2. So, if we increase the temperature, open circuit voltage decrease. If the open circuit voltage decrease, since the efficiency is proportional to the open circuit voltage, the total efficiency of the solar cell will decrease if we increase the temperature. That is why it is sometimes said that solar cell operates best at low temperature. Now, what can be the loss or the source of loss in a solar cell which contributes to the lower efficiency in a solar cell? A loss in a solar cell refers to the loss of photon energy which is not able to deliver an electron out of a solar cell. So, that means a solar radiation is falling on a solar cell, but it is not giving up an electron, the usual job of a solar cell. So, there are several ways in which photon energy can lose. One is that loss of low energy photons. The photon having energy less than the band gap energy do not get absorbed in the material and therefore do not contribute to the generation of electron hole pairs. So, let us say like a material which has a band gap like this Eg. Now, a photon which is falling on this material whose energy, if it is less than Eg or the band gap. So, if h nu is less than Eg, so then this material will not be able to absorb this photon energy. So, that photon will get lost. So, this is referred to as the transmission loss. This is referred to as the transmission loss and is almost equal to 23% for a single junction solar cells. So, to utilize a solar cell for a maximum efficiency, we need to design a material which can take care for the solar radiation both in the visible range, but both in the UV range and also in the IR range. Because most of the light, let us say, which are in a UV range, and if I have a material which has a band gap in a visible range, so then they will not be able to absorb those UV radiation. So, what it will do, that it will hit the solar cell, eventually it will decrease the efficiency of the solar cell. So, that is why we have to intelligently design the materials whenever we are designing a solar cells. Now, there can be loss due to the excess energy of the photon, just like other extreme. One extreme is the low energy of the photon, other extreme is the excess energy of the photon. When the photon energy E is higher than the band gap energy Eg. So, here the h nu is greater than Eg. So, what will happen to the fate of the electron? So, Eg is enough to take them from the ground state to the first excited state, but now we have enough energy to take them from the ground state to the excited state. What will happen to this excess energy? What is the amount of excess energy? That is h nu minus Eg or E minus Eg, that is given as a non-radiative emission, or that is given as a heat to the material. So, as we know that if we give the heat to the solar cell, then the efficiency will decrease. So, this loss is referred to as the thermalization loss. So, there can be two different loss. One is due to the low energy of the photons, that is the transmission loss, and then there can be excess energy of the photon loss, that is called the thermalization loss. Now, there can be also a voltage loss. The voltage corresponds to the band gap of a material is obtained by dividing the band gap by charge, right. So, if we divide Eg by Q, so we will get the voltage, because Eg is Q times V, and if I divide by Q, Q cancels, giving you the voltage. So, this is referred to as the band gap voltage. Now, the actual band gap voltage obtained from a solar cell is VOC, open circuit voltage. This happens due to the unavoidable Auger recombination. Fill factor loss, the IV curve of the ideal solar cell is square, fill factor is 1, but in reality the cell IV curve is given by an exponential behavior. In best case, FF can be 0.89. This type of loss arises from the parasitic resistance of the cell. As I said that if I have a higher values of the series resistance and a lower values of the shunt resistance, then fill factor changes, and looking at the fill factor we can say how good is this devices, because if the fill factor is very high, close to 1, then we have a higher efficiency. So, above mentioned loss are the fundamental loss. This cannot be avoided or cannot be minimized beyond their fundamental limits. So, from the thermodynamic Shockley-Quasar limit, we have learned that there is a limit of the maximum efficiency for a single junction solar cells, and that limit comes from the thermodynamics limit. But even for considering that thermodynamics limits, these are the sources of the loss which contributes to the lower efficiency in a solar cell. So, these losses in a solar cell can be broadly categorized into two different factors. One is the optical loss, another is the electrical loss. Now, what are the optical loss? When we make a solar cell, there can be reflection, there can be shadowing, there can be non-absorbed radiation. Let us say I have a solar cell like this. but the front surface, this is the front contact, this is the back contact. Now light is coming through here, but if the front contact is too much reflective, so most of the light get reflected rather than being transmitted. But to generate the exciton, we need the light to be transmitted through this material. So that kind of loss happens due to the reflections. Similarly, the structure of the device is such that there is a shadow effect. So we do not get the amount of the solar radiation which we intended to get, that is called shadowing. Similarly, there can be a significant amount of radiation which goes for non-absorbing, that is called non-adsorbed radiation. Now also there can be electrical loss, that can be ohmic loss or that can be recombination. Now recombination is a fundamental problem that happens due to the electron hole recombination, we cannot avoid it. We can try our best to minimize it, but there are some recombination loss that will always happen. Now what about the ohmic loss? Ohmic loss that happens due to the semiconductor material. If the material is not very pristine, if there are a lot of defects in the material, then there can be loss. It can come from the base, it can come from the emitter, it can come from the contact material. These all contribute to the series resistance. Then there can be parasitic resistance also. Now the another source is the recombination. Where can be the recombination happens? One is the emitter regions material, one is the surface base region material, another is the space charge region materials. All of these regions contribute to the recombinations. So today we learned that the different source of the recombinations which contributes to the lower efficiency of the solar cells. Once we know like the different source of the recombinations, then we can optimize those parameters so that we can get a high efficiency solar cell. That we will learn in the next chapter. For this part, we can refer to the Optoelectronics and Photonics book by S.O. Kasab and the Solar Photovoltaic books by the Chetan Solanki. Thank you.